And now in this lecture I will answer two questions. In the first question we find out the value of this angle, angle x, and in the second question we find out the area of this vein shape. So I'll start with the first question. In the drawing we have a quarter circle, AOB is a quarter circle. This is angle AOB, this is a right angle. Angle APQ is also a right angle. We know that AP equals to PQ, and our task is to find out the value of angle PQB that is equal to x. Okay, so to start in the first step, we will complete the quarter circle to a semicircle. Define this point as point M. So we completed the quarter circle to a semicircle, and therefore AM is the diameter of the semicircle according to our construction. Repeat again, AM is the diameter of the semicircle according to our construction. Write it down. AM is the diameter of the semicircle. AM is a diameter, it is absolutely a straight line. So if you focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle that is right angle. So 90 degrees plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will extend line segment PQ by a straight line until it touches the semicircle. But the question is where the extended line segment PQ will touch the semicircle. We will assume that the extended line segment PQ will touch the semicircle at this point, point L. So according to our assumption, we have here peripheral angle APL that is equal to 90 degrees inside according to what is given us the question. And peripheral angle APL subtend on chord AL. Again, peripheral angle APL definitely subtend on chord AL. but the problem is here that AL is definitely not the diameter of the semicircle, because AL doesn't pass from point O, that is the center of the semicircle, and we know that only a chord that passes from the center of the semicircle could be the diameter of the semicircle. AL doesn't pass from point O, that is the center of the semicircle, and therefore AL is not the diameter of the semicircle. But so we have contradiction to rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. In the moment we have a circle, AB is the diameter of the circle, peripheral angle A or B equals to 90 degrees in size, and therefore peripheral angle A or B must subtend on AB, that is the diameter of the circle. And indeed, peripheral angle A or B subtend on AB, that is the diameter of the semicircle, the diameter of the circle. So here, according to what is given to the question, peripheral angle in PL is a right angle, it is equal to 90 degrees in its size, and therefore it must subtend on the diameter of the semicircle. But peripheral angle APL subtend on AL, that is definitely not the diameter of the semicircle. So we have a contradiction to rule 5, and therefore we must conclude that peripheral angle APL, that the extended 90 PQ will not touch the semicircle at point L, because we have contradiction to rule 5. In the next step, we will assume that the extended 90 PQ will touch the circle at this point edge. So, according to our assumption, we have peripheral angle AP edge, and peripheral angle AP edge subtend on chord A edge. Again, peripheral angle AP edge subtend on chord A edge. Again, we have contradiction to rule 5, because chord A edge doesn't pass for the center of the semicircle, that is to say for point O, and therefore chord A edge cannot be the diameter of the semicircle. But according to rule 5, peripheral angle in PH is equal to 90 degrees in its size must subtend on the diameter of the semicircle. So we have contradiction to rule 5, and due to the contradiction to rule 5, we must conclude that the extended 97 PQ will not touch the circle at this point H, because we have contradiction to rule 5. So, therefore, we will conclude that the extended 97 PQ will touch the semicircle at this point H. Again, the extended 97 PQ will touch the semicircle at this point M. Now we don't have contradiction to rule 5. Why? Because we have peripheral angle APM that is equal to 90 degrees in its size, and peripheral angle APM subtend on AM, that is the diameter of the semicircle, exactly according to rule 5. Okay, so in the next step, we will join points A and Q together by straight line. By joining points A and Q, we created the right triangle that is also an associated triangle, triangle APQ. AP equals to PQ according to what is given as the question, therefore triangle APQ is an associated triangle, angle APQ is a right angle, and therefore triangle APQ is also a right angle. So, in the right and associated triangle, APQ, we have the rule that in front of equal sides in the triangle there are equal angles. So, in front of those two equal sides, it is given as the question that AP equals to PQ. So, in front of those two equal sides, we have those two angles that must be also equal to each other according to the rule that I mentioned. So if we define the size of this angle as alpha, define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right and associated triangle, triangle APQ? This is a right angle. Alpha plus alpha is 2 alpha, so 90 degrees plus 2 alpha must be equal to 180 degrees, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we will divide this equation by 2 and finally get that alpha equals to 90 degrees over 2, that is 45 degrees. So okay, this is angle alpha, that is equal to 45 degrees in its size. This is also angle alpha, that is equal to 45 degrees in its size. In the next step, we prove that those two right triangles can go into each other according to side angle side rule. That is to say, we prove that the upper right triangle AOQ can go into the right lower triangle OQM according to side angle side rule. So I'll write it down. We prove that triangle AOQ, this upper right triangle, can go into the lower right triangle OQM according to side angle side rule. So why those two right triangles can go into each other? First of all, side AO of the right triangle AOQ is equal to side OM of the right triangle OQM. They are both the radii of the circle and therefore they are equal to each other. So I write it down. AO equals to OM. If we define the radius of this semicircle is R, they are both equal to R. And again, side AO of the right triangle AOQ is equal to side OM of the right triangle OQM. They are both the radii of the circle and therefore they are equal to each other. In addition, those two angles are both right angles and therefore they are equal to each other. So actually, this is angle AOQ. The right upper triangle AOQ, and it is equal to this angle, that is actually angle OQM. In the right lower triangle, triangle OMQ. Repeat again. We should find out that angle AOQ in the right upper triangle AOQ is equal to angle OQM in the right lower triangle OQM. They are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side OQ, that is a common side that belongs to both triangles. So I can write down that OQ plus to itself is a common side that belongs to both triangles. Side OQ equals to itself is a common side that belongs to both triangles. So let's prove that those two right triangles can go into each other according to sine angle side rule. So write it down. We prove that the upper right triangle AOQ congruent, this is the sign of congruent, to the lower right triangle OQN, according to side angle side rule. That is to say, let's prove that those two sides and the angle that is included between those two sides in the right upper triangle AOQ are correspondingly equal to those two sides and the angle that is included between those two sides in the right lower triangle OQM. And therefore those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we derive that sine AQ of the right upper triangle AOQ is equal to side QM of the right lower triangle OQM. And again, we derive that AQ equals to QM according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides AQ and QM must be also equal to each other in their lengths. So if we found out that side EQ equals to side QM. So if we relate to the big associated triangle AQM, we have the rule that in front of equal sides in the triangle are equal angles. So in front of those two equal sides in the associated triangle AQM, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. The new rule is rule 8. According to rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. Repeat again, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. In the drawing, we have triangle ABC that could be any triangle. Those three angles alpha, beta, and gamma are defined as interior angles because they are located inside triangle ABC. Right, this is angle E that is defined as an exterior angle because it is located outside triangle ABC. And according to this rule 8, the size of the value of this exterior angle E is equal to the sum of the two interior angles that are not adjacent to it. This is the interior angle gamma that is definitely adjacent to angle E. The two other angles that are not adjacent to angle E are those two angles, alpha and beta. So the value of angle E is equal to the sum of the two interior angles that are not adjacent to it. That is to say, E equals to alpha plus beta. So the size of angle E, or the value of angle E, is equal to alpha plus beta according to this rule 8. So we can implement rule 8 in our drawing. Why? Because in our drawing, if we relate to the big associated triangle AQM, the big associated triangle AQM, those three angles are defined as the intervals of the associated triangle AQM. Well, this is angle AQP. This is located outside the associated triangle AQM, and therefore it is defined as an external angle of triangle AQM. According to Rule 8, the size of the external angle AQP is equal to the sum of the two interangles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other angles that are not adjacent to this angle AQP are those two angles, beta and beta. And therefore the size of angle AQP must be equal to beta plus beta. And again, if we relate to the big associated triangle AQM, triangle AQM is an associated triangle because side AQ equals to side QM. So in this big associated triangle AQM, angle AQP is an external angle. So the size of the external angle is equal to the sum of the two interangles that are not adjacent to it. Those are the two interangles that are not adjacent to it. That is to say, the value of the external angle AQP is equal to beta plus beta. So angle AQP equals to beta plus beta, that is 2 beta. But we have already found out that the size of this external angle AQP is equal to 45 degrees. So we can substitute angle AQP by 45 degrees. And you get that 45 degrees equals to 2 beta. Here we divide this equation by 2. And finally you get that beta equals to 45 degrees over 2 is 22.5 degrees. So actually, this is angle beta, that is equal to 22.5 degrees in its size. And this is also angle beta, that is equal to 22.5 degrees in its size. In the next step, we will focus on the right lower triangle OQM. In the right lower triangle OQM, the sum of the angles must be equal to 180 degrees. So which angles we have in the right lower triangle OQM? This is the right angle. Plus angle beta is equal to 22.5 degrees in its size, plus this missing angle, that is actually angle OQM. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So I repeat again. In the right lower triangle OQM, 90 degrees plus 22.5 degrees plus the size of the missing angle OQM, total must be equal to 180 degrees. Here we subtract 90 degrees from this equation and we get the 22.5 degrees plus the size of the missing angle OQM is equal to 180 degrees minus 90 degrees is 90 degrees. So if we found out that 22.5 degrees plus the size of the missing angle OQM, in total it must be equal to 90 degrees. Here we subtract 22.5 degrees from this equation and we get that the size of the value of the missing angle OQM, it is actually 90 degrees minus 22.5 degrees, that is 67.5 degrees. So if you found out that the size of this missing angle OQM is 67.5 degrees. So write it down. Angle OQM is equal to 67.5 degrees in its size. Here we can implement the rule that vertex angles are equal to each other. Those two angles, alpha and beta, are defined as vertex angles, and they are equal to each other in their size. That is to say, alpha equals to beta. Those two angles, 1 and 2, they are also defined as vertex angles, and they are equal to each other in their sizes. That is to say, angle 1 equals to angle 2 in its size. So you can implement the rule in our drawing. Because in our drawing we have those two angles that are defined as vertex angles, and therefore they are equal to each other in their size. That is to say, angle x equals to 67.5 degrees in its size. Angle x equals to 67.5 degrees in its size. And that is the answer to the question. If we found out that the angle that we are looking for in this question, that is angle PQB that is equal to x, is equal to 67.5 degrees in its size. And again, let me see angle x equals to 67.5 degrees in its size. So we finish with the first question. In the next step, I will present to you the second question, and we'll solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. In the drawing, we have a semicircle. The diameter PQ of this semicircle is equal to 10 units in its length. Therefore, the radius of this semicircle is equal to 5 units. So write it down. The radius of this semicircle is equal to 5 units in its length. It is half the diameter. In addition, we know that it is given us the question that inside this semicircle we have the big square ABCD and the small square MECF. Our task is to find out the area of this green shape. So first of all, we'll define the center of this semicircle. This point is point O. We'll join points O and A together by a straight line. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is of course the radius of this semicircle. It is equal to 5 units in its length. Likewise, we join points O and E together by a straight line. O is, of course, the radius of the semicircle. It is equal to 5 units in its length. ABCD is a square, and therefore this circle must be equal to 90 degrees in its size. It is 1 out of 4 angles inside square ABCD, and therefore it is a right angle. Likewise, in the small square AMEFC, this angle must be equal to 90 degrees in its size. In the next step, we will define the length of one side of square ABCD as A. So actually, AB equals to BC equals to CD equals to DA equals to A. Likewise, we define the length of one side of the small square MCEF as B. So CF equals to B, EF equals to B, EM equals to MC equals to B. We define the length of the short line segment OC as X. So what is the length of the missing line segment BO? From long it is very easy to see that BO equals to BC minus OC. So write it down. BO equals to BC minus OC. So BO equals to BC. BC is A according to our definition, minus OC. OC is X according to our definition also. So in total, BO equals to A minus X units in its length. In the next step, we will implement the Pythagoras theorem on the right triangle AOB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. The hypotenuse AO of the right triangle AOB is equal to 5 units in itself. It is also the radius of the semicircle. AB equals to A and BO equals to A minus X. So actually, this is the right triangle ABO that I copied from the original drawing. In this right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So I write it down. This will be equation 1. According to equation 1, AO squared, that is the square of the hypotenuse, is equal to AB squared plus BO squared. The hypotenuse AO equals to 5 units in its length, therefore AO squared is 5 squared, that is 25, and it is equal to AB squared. AB equals to A, therefore AB squared is A squared plus BO squared. BO is A minus X, therefore BO squared is A minus X squared. So in total, according to equation 1, we actually found out that 25 equals to A squared plus A minus X squared. In the next step, we copy the right triangle OEF in a new page and we implement on this right triangle OEF the Pythagoras theorem. Here by PT is the relation for Pythagoras theorem. What is the length of side OF for the right triangle OEF? OF in total equals to X plus B. Okay, OF equals to X plus B, let's see its length. So actually, this is the right triangle OEF that according to the original drawing. According to the Pythagoras theorem, in this right triangle OEF, OE squared, that is the square of the hypotenuse, equals to EF squared plus FO squared. So I write it down. This will be equation 2. According to equation 2, OE squared, that is the square of the hypotenuse, is equal to EF squared plus OF squared. The hypotenuse OE equals to 5 units in its length, therefore OE squared is 5 squared, that is 25. And it is equal to EF squared. EF is B, therefore EF squared is B squared plus OF squared. OF is X plus B, therefore OF squared is X plus B squared. So in total, according to equation 2, I should found out that 25 equals to B squared plus X plus B squared. This is according to equation 2, and according to equation 1, we have already found out that 25 equals to A squared plus A minus X squared. So we get equation 3 that states that 25 according to equation 1 must be equal to 25 according to equation 2. And again, according to equation 3, 25 according to equation 1 must be equal to 25 according to equation 2. Twenty-five according to equation 1 is equal to AX plus A minus X squared. And it is equal to 25 according to equation 2. 25 according to equation 2 is equal to B squared plus X plus B squared. So according to equation 3, we found out that AX plus A minus X squared equals to BX plus X plus B squared. Here we'll open the brackets on both sides of this equation 3, and get that according to equation 3, a square plus a minus x square. A minus x square equals to a square plus x square minus 2 times a times x, and it is equals to b square plus x plus b square. X plus b square equals to x square plus b square plus 2 times x times b. So here we have x square on both sides of this equation, so x square get cancelled. After cancelled x square, in this side of equation 3 we left with a square plus a square, this is 2a square minus 2ax equals to, on the other side of equation 3 we left with b square plus b square, this is 2b square plus 2bx. So here we divide this equation 3 by 2, and we get that according to equation 3, a square over 2 is a square, minus 2ax over 2 is minus ax, and it is equal to 2b square over 2 is b square, and 2bx over 2 is bx. So total according to equation 3, I should find out that a square minus ax equals to b square plus bx. Here we add ax to this equation 3, and we get that according to equation 3, a square equals to ax plus bx plus b square. So here we subtract b square for this equation 3, and we get that according to equation 3, a square minus b square equals to ax plus bx. So according to equation 3, a square minus b square equals ax plus bx. So we take x as a common factor from those two expressions, so inside the brackets we left with a plus b. So according to equation 3, I should find out that a square minus b square equals to x times a plus b. We have the famous algebraic identity that states that a square minus b square equals to a plus b times a minus b, and it is equal to x times a plus b. You know that a is the length of one side of the big square ABCD, and b is the length of the one side of the square MECF. So a and b as a length, there must be a positive number, and when you add two positive numbers to each other, the result must be a positive number. That is to say, a plus b must be a positive number. A plus b must be a positive number, it can never be equal to 0, and therefore it is allowable to divide this equation 3 by a plus b. So we divide this equation 3 by a plus b, and we get that here a plus b will get cancelled, and we left only with a minus b. On the other side of this equation 3 we have a plus b also will get cancelled, and we left only with x. So according to equation 3, we should find out that a minus b equals to x. Here we will add b to this equation 3, and finally get that according to equation 3, a equals to x plus b. Here we subtract x from this equation 3, and we get that according to equation 3, a minus x equals to b. We will square both sides of this equation, equation 3. And you get that according to equation 3, a minus x squared equals to b squared. And again, I should find out that according to equation 3, a minus x squared equals to b squared. Our task is to find out the area of this green shape. So what is the area of the green shape? From the dominant, it's very easy to see that the area of this green shape equals to the area of the semicircle minus the area of the big square ABCD minus the area of the small square MEFC. Repeat again. The area of the green shape in total equals to the area of the semicircle minus the area of the big square ABCD minus the area of the small square. What is the area of the semicircle? The area of any semicircle equals to the area of the circle over 2. And therefore the area of this semicircle must be equal to pi r square over 2. But we have already found out that the radius of this semicircle r equals to 5. So pi r square is pi times pi square over 2, that is actually 25 pi over 2. So if we found out that the area of this big semicircle is equal to 25 pi over 2 square units in its size, minus the area of the big square ABCD. We know that one side of this big square ABCD is equal to a units, and therefore the area of this square must be equal to a square. So it is minus a square minus the small square, MEFC. We know that one side of the small square is b, therefore the area of the small square is b square, so it is minus b square. So if we found out that the area that we are looking for in this question, this is the area of this green shape, is equal to 25 pi over 2 minus a square minus b square. So it is 25 pi over 2 minus, we take minus 1 as a common factor for those two expressions. So inside the brackets we left only a square plus b square. So in total we have found out that the area of the green shape equals to 25 pi over 2 minus a square plus b square. According to equation 1, we have already found out that 25 equals to a square plus a minus x square. 25 equals to a square plus a minus x square. But according to equation 3, we have already found out that according to equation 3, we already found out that a minus x square equals to b square. So actually, we can substitute a minus x square in this equation 1 by b square from equation 3. We do it now, then we get that according to equation 1, 25 equals to a square plus a minus x square. A minus x square according to equation 3 is b square. So we substitute a minus x square by b square. So in total we found out that according to equation 1, a square plus b square equals to 25. Therefore, we can substitute a square plus b square, this expression, by 25. So this is equal to 25 according to equation 1. We do it now, we get that there of the Greensham in total it is equal to 25 pi over 2 minus a square plus b square, and a square plus b square according to equation 1 is 25. So in total we found out that the area that we are looking for in this question, that is the area of this green shape, it is equal to either 25 pi over 2 minus 25 square units in its size. On terms of numbers, the value of this expression in total is equal to 14.27 square units in its size. Repeat again, I shall find out that the area that we're looking for in this question, that is the area of the green shape, equals to either 25 pi over 2 minus 25 square units in its size. On terms of numbers, the area of this green shape equals to 14.27 square units in its size. So we finish with the first question. In the next step I summarize the lecture. We start with the first question, of course. In the first question, our task was to find out the size of this angle x, the angle PQB. So in the drawing, we have a quarter circle. This is angle AOB, that is a right angle. This is angle APQ, that is also a right angle. In addition, we know that AP equals to PQ. Again, our task is to find out the size of this angle, and angle x is equal to angle PQB. We have to find out the value of x. So first of all, we completed the quarter circle to a semicircle, and we define this point as point M. So actually, AM is the diameter of the semicircle according to our construction. Repeat again, because of the fact that we completed the quarter circle to a semicircle, AM must be the diameter of the semicircle according to our construction. So AM is a diameter, it is absolutely a straight line. So if you focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle that is a right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, I extended line segment PQ until it touches the semicircle. But the question is, where the extended line segment PQ will touch the semicircle? We will assume that the extended line segment PQ will touch the semicircle at this point N. So according to our assumption, we have a peripheral angle APL that is equal to 90 degrees in its size according to what is given as the question, and peripheral angle APL subtend on chord AN. Again, peripheral angle APL subtend on chord AN. But the problem is that AN is not the diameter of the circle. Why chord AN is not the diameter of the circle? Because it doesn't pass from point O, that is the center of the semicircle. We know that any chord, only a chord that passes through the center of the circle could be the diameter of the circle. AL doesn't pass from point O, therefore it is not the diameter of the semicircle. Therefore we have contradiction to rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its size, exactly like this peripheral angle APM that is equal to 90 degrees in its size according to what is given in the question, must subtend the diameter of the circle. But peripheral angle APL subtend on chord AM, that is not the diameter of the semicircle. So we have contradiction to rule 5, and therefore we will conclude that the extended line segment PQ will not touch the semicircle at point A. In the next step, we assume that the extended line segment PQ will touch the semicircle, will touch the circle at this point, point H. So according to our assumption, let's say the PQ touch the semicircle at point H, and therefore we have here peripheral angle APH. Peripheral angle APH is right angle according to what is given in the question, and peripheral angle APH subtend on chord AH. It is very easy to see that peripheral angle APH subtend on chord AH. But the problem is that chord AH is not the diameter of the semicircle because it doesn't pass through point O, that is the center of the semicircle. And therefore AH is not the diameter of the semicircle. It is contradiction to all 5 because peripheral angle APH must subtend on the diameter of the semicircle, but it subtend on the edges is not the diameter of the semicircle. So we have contradiction to all 5, and therefore we conclude that the extended line segment PQ will not touch the semicircle at point H, will not touch the circle at point H, due to the contradiction to all 5. And therefore we must conclude that the extended line segment PQ will touch the semicircle at point M and not in any other point. Now we don't have contradiction to all 5. One, because we have peripheral angle APM that is equal to 90 degrees in its size, and indeed it subtends on the diameter AM exactly according to all 5. In the next step we join points A and Q together by straight line. By joining points A and Q, we can get the associated right triangle, triangle APQ. In the right hand associated triangle APQ, we have the rule that in front of equal sides in the triangle there are equal angles. Again, in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, side AB equals to side PQ according to what is given in the question. So in front of those two equal sides in the right hand associated triangle APQ, there are those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And you know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in the right hand associated triangle APQ is equal to 180 degrees. So which angles we have in the right hand associated triangle APQ? We have this angle that is a right angle. Alpha plus alpha is 2 alpha, so 90 degrees plus 2 alpha must be equal to 180 degrees. Here we subtract the 90 degrees from this equation, and we found out that 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we divided this equation by 2, and we found out that 90 degrees over 2 is 45 degrees. This is angle alpha, this is equal to 45 degrees in its size. This is also angle alpha, this is equal to 45 degrees in its size. In the next step, we prove that those two right triangles can go into each other according to side angle side rule. That is to say, we prove that the right upper triangle, triangle AQO, can go into the right lower triangle, triangle OQM, according to side angle side rule. So why those two right triangles can go into each other? First of all, side AO of the right triangle AOQ is equal to side OM of the right triangle OQM. They are both the radius of the semicircle, and therefore they are equal to each other. So we define the radius of the semicircle as R, then AO equals to R, and also OM equals to R. In addition, those two angles are both right angles, and therefore they are equal to each other. And finally, side OQ is a common side that belongs to both triangles. So we can write down that OQ equals to itself as a common side that belongs to both triangles. So if we prove that the upper right triangle AOQ can go into the right lower triangle OQM according to side angle side rule. And again, if we prove that the right upper triangle AOQ can go into the right lower triangle OQM according to side angle side rule. That is to say, we prove that those two sides and the angle that is included between those two sides in the right upper triangle AOQ are corresponding equal to those two sides and the angle that is included between those two sides in the right lower triangle, triangle OQM. And therefore those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive that side AQ of the right upper triangle AOQ is equal to side QM of the right lower triangle, triangle OQM. Then we derive that AQ equals to QM. AQ equals to QM according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. So we found out that AQ equals to QM. So if you relate to the big associated triangle, triangle AQM, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule 8. According to rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. In the drawing, we have triangle ABC that could be any triangle. Those three angles alpha, beta, and gamma are defined as any triangles because they are located inside triangle ABC. While this is angle E, that is defined as exterior because it is located outside triangle ABC. And according to this rule 8, the side of the exterior angle E is equal to the sum of the two interior that are not adjacent to it. This is the interior angle gamma that is definitely adjacent to angle E. The two other angles that are not adjacent to angle E are those two angles alpha and beta. And therefore, according to rule 8, the value of angle E is equal to alpha plus beta, or the side of angle E equals to alpha plus beta. That is the sum of the two interior that are not adjacent to E, to angle E. So angle E equals to alpha plus beta. We can implement rule 8 in our drawing. One, in our drawing, if we focus on the big associated triangle, triangle AQM, those three angles, beta, this angle beta, defined as interiors of this associated triangle AQM, while this is angle AQP, that is defined as an exterior because it is located outside triangle AQP, outside the associated triangle AQM. So according to rule 8, the size of the exterior angle AQP equals to the sum of the two interiors that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other angles that are not adjacent to angle AQP are those two angles. Therefore, according to rule 8, the size of the exterior angle AQP is equal to beta plus beta. And again, if you focus on the big associated triangle AQM, according to rule 8, the size of the exterior angle AQP is equal to the sum of the two interiors that are not adjacent to it. That is to say, this is equal to beta plus beta. Beta plus beta is to beta, so the size of the exterior angle AQP equals to 2 beta. But we already found out that the size of this exterior angle AQP is equal to 45 degrees, so we can substitute the exterior angle AQP by 45 degrees, and we get that 45 degrees equals to 2 beta. Here we divided this equation by 2 and finally found out that beta equals to 45 over 2 is 22.5 degrees. So this is angle beta, this equals to 22.5 degrees in size, and this is also angle beta, this equals to 22.5 degrees in size. In the next step, we focus on the right lower triangle, triangle OQM. The sum of the angles in this right lower triangle, triangle OQM, must be equal to 180 degrees. So which angles we have in the right lower triangle OQM? We have this angle that is 90 degrees, plus this angle beta that is equal to 22.5 degrees in size, plus this missing angle OQM, total must be equal to 180 degrees. Okay, again, in the right lower triangle OQM, the sum of the angles must be equal to 180 degrees. That is to say, 90 degrees plus angle beta that is 22.5 degrees in size, plus the missing angle OQM in total must be equal to 180 degrees. Here we subtract the 90 degrees from this equation and finally found out that 180 degrees plus 90 degrees is 90 degrees. So 90 degrees equals to 22.5 degrees plus the side of the missing angle OQM. Here we subtract 22.5 degrees from this equation and finally found out that the side of the missing angle OQM is equal to 90 degrees plus 22.5 degrees. 90 degrees plus 22.5 degrees is 67.5 degrees. So if you found out that the size of this missing angle OQM is equal to 67.5 degrees. In the next step, we implemented the rule that says that vertex segments are equal to each other. In the drawing, those two angles alpha and beta are defined as vertex segments and they are equal to each other in their size. That is to say, alpha equals to beta. Those two angles are also defined as vertex segments and therefore they are equal to each other in their size. That is to say, angle 1 equals to angle 2. So you can actually implement the rule in our drawing because in our drawing we have those two angles that are defined as vertex angles and they are equal to each other. That is to say, angle x equals to 67.5 degrees in size. So if you found out that the angle that we are looking for this question is angle x that equals to 67.5 degrees in size. This is the missing angle PQB is equal to x and it is equal to 67.5 degrees in size. So we finish with the first question. In the next step, I presented to you the second question and we solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the drawing, we have a semicircle. We know that the diameter PQ of this semicircle equals to 10 units in its length, therefore the radius is equal to 10 over 2, that is 5. So the radius of this semicircle equals to 5 units in its length. In addition, it is given us the question that inside this big semicircle we have the big square ABCD and the small square MEFC. Again, our task is to find out the area of this green shape. So first of all, we define the center of this semicircle. This point is point O. We join points O and A together by straight line. Point O is the center of the semicircle, point A is the point on the semicircle itself, therefore OA is the radius of the semicircle that is equal to 5. Likewise, OE is also the radius of the semicircle that is equal to 5. We define the one side of the big square ABCD is A, therefore AB equals to AD equals to DC equals to CB equals to A. Likewise, we define the length of one side of the small square as B. So CF equals to B, FE equals to B, EM equals to B, and MC also equals to B. We define the length of this short line segment OC as X. So what is the length of the missing line segment OB? OB equals to BC minus OC. Again, OB equals to BC minus OC. So OB equals to BC, that is A, minus OC, that is X. So in total, OB equals to A minus X units in its length. In the next, so in the big square ABCD, this angle is a right angle, and the small square MEFC, this angle is also a right angle, because it is 1 out of 4 angles inside square ABCD, that it must be a right angle. In the next step, we implemented the Pythagoras theorem on the big right angle, triangle ABO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So according to the right triangle ABO in a new page, we implemented on this right triangle ABO the Pythagoras theorem. Okay, this is the right triangle ABO that according to the original drawing. This right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is 5, therefore AO squared is 5 squared, that is 25, and it is equals to AB squared. AB is A, therefore AB squared is A squared, plus BO squared. BO is A minus X, therefore BO squared is A minus X squared. So in total, according to equation 1, we have found out that 25 equals to A squared plus A minus X squared. Likewise, I copied right triangle OEF in a new page, and we will implemented the Pythagoras theorem on this right triangle OEF. So okay, this is the right triangle OEF that I copied from the original drawing. Here by PT is a version for Pythagoras theorem. According to the Pythagoras theorem in this right triangle OEF, OE squared, that is the square of the hypotenuse, equals to EF squared plus OF squared. OE is 5, therefore OE squared is 5 squared, that is 25, and it is equal to EF square. EF is B, therefore EF square is B square plus OF square. OF is X plus B, therefore OF square is X plus B square. So in total, according to equation 2, we found out that 25 equals to B square plus X plus B square. This is according to equation 2. And according to equation 1, we have already found out that 25 equals to A square plus A minus X square. In the next step, we can add equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. Then again, equation 3 says that 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to A square plus A minus X square. And it must be equal to 25 according to equation 2. 25 according to equation 2 equals to B square plus X plus B square. We open the brackets on both sides of this equation 3 and found out that A square plus A minus X square equals to A square plus X square minus 2 times A times X. And this equals to B square plus X plus B square. X plus B square equals to B square plus X square plus 2 times X times B. Here we have X square on both sides of this equation 3, so X square we get cancelled. After cancelled X square, in this side of the equation 3 we left with A square plus A square, that is 2A square minus 2AX. Right? In the other side of this equation 3 we left with B square plus B square, that is 2B square plus 2XB. Here we divided this equation 3 by 2 and finally found out that 2A square over 2 is A square, minus 2AX over 2 is minus AX, and it is equals to 2B square over 2 is B square, and 2BX over 2 is BX. So in total, according to equation 3, we found out that A square minus AX equals to B square plus BX. Here we added AX to this equation 3, and finally found out that according to equation 3, A square equals to AX plus BX plus B square. Here we subtracted B square from this equation 3, and finally found out that according to equation 3, A square minus B square equals to AX plus BX. So here we took out a common factor, we took X as a common factor from those two expressions. So inside the brackets we left with A plus B. So in total, according to equation 3, we found out that A square minus B square equals to X times A plus B. We have the famous algebraic identity that says that A square minus B square equals to A plus B times A minus B, and it is equals to X times A plus B. A and B are the lengths of the sides of the squares, the big square BCD and the small square MEF and CEF, and therefore they are absolutely positive numbers. So when you add two positive numbers to each other, the result must be a positive number. And therefore A plus B is a positive number, and therefore it is allowable to divide this equation 3 by A plus B, because it can never be equal to 0. It must be a positive number. So we divided this equation 3 by A plus B. So here A plus B we get cancelled, and we left only A minus B. Here A plus B also we get cancelled, and we left only with X. And according to equation 3, we found out that A minus B equals to X. Here we added B to this equation, and finally found out that A equals to X plus B. Here we subtracted X from this equation, and finally found out that A minus X equals to B. Here we squared both sides of this equation 3, and finally found out that A minus X square equals to B square. Repeat again, according to equation 3, we actually found out that A minus X square equals to B square. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total equals to the area of the semicircle minus the area of the big square BCD minus the area of the small square MEFC. Repeat again. The area of the green shape in total equals to the area of the semicircle minus the area of the big square BCD minus the area of the small square MEFC. The area of the semicircle equals to the area of the circle over 2. That is to say, it is equals to pi r square over 2. But r is 5, so pi r square over 2 is 25 pi over 2 minus the area of the big square BCD. One side of the big square BCD is A, therefore the area of the big square is A square, so it is minus A square. One side of the small square MEFC is B, therefore the area of the small square ABCD is B square, so it is minus B square. So in total, we found out that the area of the green shape equals to 25 pi over 2 minus A square minus B square. So it is 25 pi over 2 minus, so we took minus 1 as a second factor from those two expressions, so inside the brackets we left with a squared plus b squared. So in total we found out that the area of the green shape equals to 25 pi over 2 minus a squared plus b squared. According to equation 1, we have already found out that 25 equals to a squared plus a minus x squared. While according to equation 3, we have found out that a minus x squared equals to b squared. Again, according to equation 3, found out that a minus x squared equals to b squared. So, we can substitute a minus x squared by b squared from equation 3. We did it, and we found out that according to equation 1, 25 equals to a squared plus a minus x squared. And a minus x squared equals to b squared according to equation 3. So 25 equals to a squared plus b squared. So we can substitute a squared plus b squared by 25 from equation 1. We did it, and we actually found out that the area of the green shape in total equals to 25 pi over 2 minus 25. So the area of the green shape in total equals to either 25 pi over 2 minus 25 square units, or in terms of numbers, the value of this expression is 14.27. So the area of the green shape equals to 14.27 square units in its size. Repeat again, the area of this green shape, it is the area that we are working for in this question. It is equal to either 25 pi over 2 minus 25 square units in its size, or in terms of numbers, the area of this green shape is equal to 14.27 square units in its size. Okay, thank you very much.